going to slide you over there just a little bit because during our little break here, it occurred to me I wanted to show you that you can indeed filter the output of show IPv6 interface by putting the name of the interface that you want to see IPv6 information for. It's kind of a long-winded explanation, but you get the gist of it. Now, of course, on the router right now, we have one interface enabled with IP version 6, so I was just running show IPv6 interface to get you used to that. But as you get more and more interfaces on your router with IP version 6 running on them, then you might want to filter it a little bit just by putting the interface name at the end. So let's see, what is the deal with these link local addresses? Where did that come from? And what is its purpose? Sounds like we're talking about UFOs. You know, where do they come from? Why are they here? Well, let's see what the link local address is all about and why it's here. The name is the recipe. It is a link local address. Packets sent to a link local address never leave the local link, and by that I mean that a router will not forward them. They can't forward them actually. So these packets that go to a link local address, they literally cannot leave. Now these are unicast messages, by the way, and a quick review of those terms. Unicast means it's destined for one host. Multicast, which we've seen a little bit of here in version 6, we saw those groups. We'll talk more about those. But a multicast is destined for a group of hosts, a defined group. And then finally we have a broadcast that is destined for everybody, except in version 6 we don't have broadcast, but we do have them in version 4. Just wanted to review those three terms right now. Now, the router created the link local address on its own. You and I didn't do that, and it does so in accordance with a few simple rules. And we're going to see those in action, and that address has been compressed, the one that we saw on the router, and that's been compressed along with a few other simple rules. We know those: zero compression, leading zero compression. But we also need to know how to uncompress an address, and we did a little of that, but let's do some more here. Here is the compressed address. What's it going to look like when you uncompress it? There are two steps to this, and it really doesn't matter which order you do them in because you're going to get the same answer, and it will be the right one. First, what I like to do is undo the leading zero compression first. Any block that has fewer than 4 characters, you've got to put 4 values. You've got to put zeros in the front until each block has 4 values. And I see 3 blocks here that don't have 4 values. So you put zeros in the front until each one of those has 4 values in it. Now the double colon, we know that's zero compression, and we know that's representing full blocks of zeros, but how many? We should have 8 blocks in our address. We have 5 right now, so you put 3 in. See, nothing to it. There's your compressed address that we started with. There's the uncompressed address, and we're ready to move forward. Now, the first part of that address, the first half, comes from the link local reserved address block, and this is a good one to know. It's FE80:10. Now, that mask means the first 10 bits have to match FE80. So I've broken that down into binary, and the interesting thing here is that those last 2 values, the last 2 bits in the third block, we could come up with 4 different combinations there because those don't have to match the 10-bit mask. They're the 11th and 12th bits, so they don't have to match. And we could have 00, 01, 10, and 11. So theoretically, that means that link local addresses should be able to begin with FE8, 9, A, and B. And you know where we're getting those values from, and I'm going to show you anyway. And you can see here we could come up with 8, 9, A, or B. Of course, that would be 10 and 11 in decimal, but we're using hex here. So 1010, that's 8 plus 2, that's your A, and then 1011, that's 8 plus 2 plus 1, that's your 11, and that's your B. I did say theoretically, didn't I? Well, the request for comments, which is a highly technical document that you're welcome to go out and read, you don't need to do so for the exam, but you are going to see these RFCs referred to from time to time. And this is RFC 4291. And it states the last 54 bits of a link local address should all be set to 0. Well, out of these 4 values, the only one that allows that is the 8. Because if we have even 9, if we go 1 higher, then with that setup, with 1001 as the third octet, the last 54 bits would not be set to 0. It would be the last 52 bits. So the only value that meets the RFC 4291 requirement is FE80. So here's the good part of all of this. I know I'm hitting you with a lot of theory here, but here's the good part. All link local addresses begin with FE80 followed by 3 blocks of zeros. But again, that's a good reserved address block to know, FE80:10, the link local reserved address block. Now we are halfway there, because if we take a look at our link local address, we see FE80 right there at the beginning and zero compression right after it. We see 5 blocks overall. So we know that the zero compression is representing 3 blocks. So far the theory holds up because the link local address is FE80 followed by 3 blocks of zeros. So far everything is beautiful. Now the second half of the link local address is the 64-bit interface identifier. And the most common way to get that value is to allow the router to create it via EUI64 rules. Do not panic. That sounds really complicated, right? It's an IEEE standard, and it's not a huge complicated set of rules we have to learn. We just need to know EUI64 is creating this interface identifier. We'll work with it a little bit more in this section of the course. But the big deal right now is to look at this process overall, this interface identifier creation process, and we're going to compare it to the identifier we see on our router. Because when you come back for the beginning of the next video, we're going to do a walkthrough first with these rules about how Cisco routers create interface identifiers, and then we'll do another one and compare it to what we see on our real-world router, and that is all coming up next.